Okay, I apologize for that. I honestly have no clue what happened, but I'm not going to mess. I'm going to keep it here. I'm not going to click on anything. Okay, so let's go back to that social commentary I made. I think now I illustrated why I said that little thing, and I think yet again it illustrates just the genius of the statement I made. Okay, I apologize for this. So let's go back to here. So we have this here, and hopefully I haven't lost anyone here. It looks like everyone's pretty much here anyways. Okay, so this is good. Okay. So now we take our current here and we put this into here. And so this is going to be our, this actually was up here that we had this. So we have our 3/2 pi, r to the 4th minus a to the 4th here, then plus I like that. I divide through by my 2 pi r, and then that would be my b. So my b would be mu naught 3/2 pi, r to the 4th minus a to the 4th, plus I. I got my I here. I'm going to squeeze you a little bit, Sarah. I'll fix that for the next class. Okay, over 2 pi r, like that. That's what we'd have for there. Now, how are we doing on time? Okay, better than I thought it would be after that stupidity on my part. Okay, so we have that. Now we have the one last region here. We would now want to be outside B. So we want to go for r greater than B. So what do we do? Tell me why we have everything done. And if we're careful, there's absolutely no more work. So tell me why that's the case. And I need the chat box up. Yeah, all you have to do is change the R with the B. Now you have to be careful. You don't do the following. Don't come to this equation here and say, oh, I'm going to take this, make this B, and make this B. That won't work. What you have to do is you have to come back to this expression here and change this R to B. So in other words, when we have this right here, we have this guy. And what do we know about this? This right here has to be my B 2 pi r. All right, that doesn't change because again, I'm going to erase some of this here. And I'm going to make a smaller version of it so you can see. So in this case, what do we have? Here's our inner wire, here's our A, here's our outer wire, here, this is our B. Now this R here, we're outside this, and so this is my R here. So that's how I'm getting this 2 pi r here. Now I need the total current contained within this Amperian loop, and so that's going to be this current here, plus that current here. That means I have to come back to this I enclosed expression. And what do? I have the exact same thing, but I have to change the limit on this radius here, instead of being little r here, to being b. And if you do that, then you end up with the same thing we had before. And so this would be, and I erased it because I didn't have it with me. So before we had this I enclosed was this 3 pi r to the 4th over 2 minus a to the 4th plus I. That's really sad. And so what we do is we change that one here to a b. So this gives me mu naught 3/2 pi b to the 4th minus a to the 4th plus I. That's what we'd have now. So then if we then solve for the b here, we get mu naught 3/2 pi b to the 4th minus a to the 4th plus I, all over 2 pi r. There. That would be my expression for the magnetic field outside B. Does that make sense? And that's about as hard as these things are going to get. Okay, so that said, we are now done. Oh, hang on. Sounds good. Okay. So we are now done with Ampere's law. And so what we're going to do, we're going to get the last two Maxwell's equations. We're going to get one tomorrow. This one does not have a name. It has no name to it. And we're going to deal with magnetic flux. And so let's say a little bit about what we mean by flux. Remember when we have flux, what we do, we construct an imaginary surface. So here's an imaginary surface like this. And again, remember that's, that'd be, let's see, so let's say here's my little thing I've been wiping the thing with. I need a closed surface. So remember with this, if I wrap this up like this, kind of go like this and tuck it all in here like that. Okay, this right here would be a closed surface. So imagine this surface here represents the outer surface of this paper towel that I folded on itself. And then what did we do? We had some vector like this. We called that V. And how did we define the vector? We drew a tiny little patch of area on that surface. And we drew our little area vector. Remember that area vector by definition is outward and perpendicular. So this is dA. This is our tiny little patch of area. We ask how much of that vector pokes out along here. That means a dot product. And that's what we mean by flux. And so the flux through dA is really this V dot dA. If I wanted the total flux, what did you have to do? You had to integrate over this entire surface. And that's remember, a surface actually involves two integrals because you have to integrate in both directions. And we have to go over the entire surface, so we need two integrals. So I put two little integrals there. And I have to go over the whole surface, and so I put that little loopy thing there. And I say V dot dA, and this is my total flux of V through the surface. Like that. Now, what we're going to do is, and tomorrow we're going to let this be the magnetic field. And I'm going to set this all up again. So the V is going to become the magnetic field tomorrow, and we're going to work out the flux for this magnetic field. And it turns out that no matter what magnetic field you have, with the exception of one case, which is very important, that will always equal 0. So what we're going to find out tomorrow is that if you look at the total magnetic flux around a surface, this is always equal to 0. There would be one case which has not been discovered where this would not be 0. And I can guarantee you, if you find that case, you'll be going to Stockholm that year, the very year, with a Nobel Prize in physics. And so I want to talk about the implication of that. We can't do a whole lot with this law here. I'm going to mention it. We're going to do some problems with it. We can't do a whole lot with it, but it is one of Maxwell's equations, and it is important. And then we're going to get a more important one, and this is called Faraday's law. And then that's where all the really profound, a lot of the applications we have for electricity and magnetism comes entirely from Faraday's law. And so we're going to spend a long time hitting that really, really hard. Okay, so have a good day. Stay safe and healthy. I apologize for the technical issues, as I suspect it's not going to be the last of these. But have a great day. Bye-bye.